Hi everybody, in this video we are going to go over section 2 of chapter 6, and in here, this section we are going to introduce the unit circle and also the circular functions, which will look a lot like the trigonometric functions, but just expressed in a different context. So, we're going to first talk about the unit circle, then the functions, and how we can compute the values of those functions using the unit circle and the calculator. And then we will also talk about how to find inverse circular functions, i.e. given the value of a circular function, what is the arc length or the angle associated with it. Finally, we will apply circular functions to the concepts of linear and angular speed. Okay, so the figure to the left here is a unit circle. Notice that it crosses the coordinates 1, 0, 0, 1, negative 1, 0, and 0, negative 1. As a consequence, it has a radius of 1 unit, whatever that unit might be. Of course, it is centered at the origin, so as a consequence, what we've learned from 115, the equation that defines this circle is x squared plus y squared is equal to 1. Now, the arc length of this circle is equal to, as we know, r times theta. However, the radius is equal to 1, so it turns out, for the case of the unit circle, the arc length is equal to theta. So if theta is equal to pi over 3, you guessed it, this arc length is also pi over 3. So what else can we say about the circle? Well, check this out. It is symmetric with both the x-axis and the y-axis and also the origin, just like any other circle which is centered at the origin. Also, if point AB, any point lies on the line, then not only does AB lie on the line, negative A, positive B lie on the line. The coordinate negative A, negative B lies on the circle, not the line, the circle. And finally, the coordinate A, negative B also lines on that circle. Also, each of these points has a reference arc of equal magnitude. Now, what is a reference arc? Well, a reference arc is basically the shortest arc from that particular point to the x-axis. So you can kind of see the reference arc for AB. If we were looking at this point, this would be the reference arc. This would be the reference arc for the same point for negative AB. This would be the reference arc for negative A, negative B. And of course, this would be the reference arc for A, negative B. To show this a little more clearly, here we go. Here we have an arc of pi over third, so this angle is pi over third, and the coordinate on the unit circle associated with that angle and also that arc is 1/2 root 3 over 2. Okay, well, here is AB, here is negative AB, here is negative A, negative B, and here is A, negative B. And these are the reference arcs, and notice they are the exact same length. So that's pretty much all we're saying here is that if AB lies on the unit circle, then these will, and they all have the exact same reference arc, i.e. the shortest arc from that point to the x-axis. Okay, and with that, we can define the circular functions and check it out. They are the 6 trig functions, and they're pretty much defined the exact same way. We're just talking about a different context. Here, S is the arc length on the unit circle. Since it's a unit circle, the value of S equals the value of theta. In other words, the angle required to intercept that particular arc. So as a consequence, the sine of S is equal to the sine of theta, which would be y over r, but r is equal to 1, so it's just y. Similarly, we have cosine of S being equal to x using the exact same argument. And of course, then everything else applies. The inverses are pretty straightforward. We have the tangent being y over x, and the cotangent being x over y. And notice that tangent and secant are not defined whenever x is equal to 0. So if you are here or here, they are not defined. And notice those angles would be 0, pi, 2 pi, 3 pi, and so forth. And of course, then cosecant and cotangent are not defined when y is not equal to 0, or whenever the angle or the arc length is pi over 2, 3 pi over 2, 5 pi over 2, and so forth, i.e. they are not defined for any odd multiple of pi over 2. Now, the next thing we want to do is talk about this particular table. We want to talk about S, the three reference angles, and how they correspond to the original arc length or the original angle S. So let's get started. Our first angle, or arc length is pi over 3. Here it is. It lies in quadrant 1. And of course, the point associated with that is 1/2 root 3 over 2. As a consequence, the cosine of pi over 3 is the x value, which is 1/2, and the sine of pi over 3 is root 3 over 2. All right, now let's take a look at pi minus pi over 3. That is this particular point here, pi minus pi over 3. Notice that this point lies here, and we have symmetry about the y-axis. So this is symmetric about the y-axis, and this, of course, is the point. Okay? As a consequence, cosine is going to be negative x, which is negative 1/2, and sine is still root 3 over 2. So what we're doing is we're trying to find other values on this unit circle based upon this particular reference value. So the next value is going to be pi plus pi over 3. And that puts us right here. So here's pi over 3, here's pi plus pi over 3. Notice that those 2 points on the unit circle are symmetric about the origin. As a consequence, since this is 1/2 root 3 over 2, this is negative 1/2 root 3 over 2. And we can see that cosine of pi plus pi over 3 is negative 1/2, and the sine is negative root 3 over 2. And then finally, if we want to look at 2 pi minus pi over 3, well, basically that's 2 pi minus this angle. That puts us here. Notice that we have symmetry about the x-axis now. And so then the cosine value, of course, is plus 1/2, and the sine value is negative root 3 over 2. So that's the thought process behind filling out this table. Okay, so let's go ahead and talk about some domains. First domain is, well, the sine and cosine. Well, notice that the sine of s is equal to y, and cosine of s is equal to x. And also notice that x and y can basically travel all the way around this unit circle for as much as it wants. As a consequence, sine and cosine are defined for every single value of x and y, and therefore the domain is the entire real line. Well, what about tangent and secant? Well, tangent and secant are defined for every single value of s except for those values of s where x happens to be 0. Okay, so when does that occur? Well, that occurs whenever we are on the y-axis, and that occurs when s is pi over 2, or 3 pi over 2, or any odd multiple of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, go on and so forth. As a consequence, the domain of tangent and secant is all values of s such that s is not equal to, and this is the formula for any odd integer, times pi over 2, where once again n can be any possible integer. And then finally, notice here that the cosecant and secant of s are undefined when y is equal to 0, okay? And that occurs whenever s is equal to some multiple of pi, okay? Whenever s is here, 0, pi, 2 pi, and so forth, y is equal to 0, and these are undefined. So the domain of cotangent and cosecant would be all values of s except for those values of s which is some integer multiple of pi. This basically means s such that s is not equal to n times pi, where n is a member of the integers. Well, how do we compute the values of circular functions? Well, since basically the circular functions are really nothing more than trig functions expressed in a different context, we compute them in the exact same manner. And of course, since we are working on a unit circle and we are dealing with an arc length which is related directly to angles in radians, the calculators must always be in a radian mode. Okay, so let's have some fun. Here we want to find some exact circular values. So we want to use the unit circle to find the exact values of the sine of 4 pi over 3 and the cosine of 4 pi over 3. Well, here's our unit circle. Look over here. Here's 4 pi over 3. I already have it circled for you. And remember, and as a consequence, this is x and this is y. What is sine of 4 pi over 3? Well, that's going to be equal to y. In this case, it is equal to negative root 3 over 2. Cosine of 4 pi over 3, exact same thing. Cosine of 4 pi over 3 is equal to x. Well, x in this case is negative 1/2. There you go. You're done. Okay, now we want to find the unit circle, or we want to use the unit circle to find the exact value of tangent of negative 9 pi over 4. So, how do we do that? Well, let's start here, where theta is equal to 0, and we are going to rotate, we're going to go around the unit circle 9 pi over 4 radians. So let's go ahead, or we're going to trace an arc length of negative 9 pi over 4, which basically means we're going to go in the negative direction, which in this case is clockwise. So here we are at 0. This is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4. It puts negative 9 pi over 4 puts us right there. So this is the angle, or the angle and the arc associated with negative 9 pi over 4. Turns out it's equal to 7 pi over 4. So we have that the tangent of negative 9 pi over 4 happens to be equal to the tangent of 7 pi over 4, because it comes to the exact same point on the unit circle. And that is going to be equal to y over x, which in this case is equal to negative root 2 over 2 divided by root 2 over 2, which of course is negative 1. And there you go. And finally, in this one, we want to use reference angles and radian to degree conversion to find the exact value of sine 11 pi over 6. So let's go off and first use radian to degree conversion. We have theta, which is 11 pi over 6. To convert that to degree, we need to multiply that by 180 degrees divided by pi radians. And if we do, we will have 330 degrees. Okay, now 330 degrees lies in quadrant 4. So this is in quadrant 4. Its reference angle is 30 degrees. To draw a rather poor picture, here is my circle. Rather poor excuse of a circle, sorry about that. This right here is 330 degrees. And the reference angle is 60. Okay, now what we know from reference angle analysis is that if it's in quadrant 4, then since 330 is in quadrant 4, it turns out that the sine of 330 is going to be equal to negative sine of 160. That's not sine of 160, but sine of 30. The sine of 30 is equal to 1/2, so this is going to be equal to negative 1/2, and that would be our answer. Of course, another way you could do that, I mean, basically for this particular problem, I was essentially strictly following these directions. However, another way to do this is, check it out, 11 pi over 6, well, there it is. That's 11 pi, well, let me try this one. 11 pi over 6, there it is, it's right here. Okay, what's the sine of 11 pi over 6? Negative 1/2. In this example, we want to find the calculator approximation for these two values. So how do you do that? Well, you go ahead and you use your calculator. Now for each of these, we are going to compute these to 4 decimal places. All right, for this one, it is pretty straightforward. We just basically put sine of 3.42 in our calculator, and if we do, we will have negative 0.2748. Those are our 4 decimal places. Let's take a look at the fifth. It is a 2, so this will round to negative 0.2748, and we're done. Okay, for the next one, well, you'll notice that we really don't have secant on our calculator. However, we do have cosine, and it turns out that the secant is equal to 1 over the cosine. And if you punch that out, you will have that this is equal to 1.2851. Those are our 4 decimal places. The fifth one is a 0. Well, that makes it pretty easy. This is just going to be 1.2851. Okay, the next thing we're going to need to do is actually approximate the value of is find the numbers associated with the circular function value. So here we have sine of s is equal to 0.3210, and we want to find what the value of s is. And of course what we're going to do is we are going to use the inverse function on our calculator, which will be sine negative 1. Let me just go ahead and put the number in, 0.3210. And if we do, we will get 0.3267. Those are our 4 decimal places. So let's look at the fifth. It's greater than 5, so this will round to 0.3268. Now, one of the things I want you to notice here is that we have that the sine of 0.3210, the inverse sine, is, or the arc sine, is equal to 0.33268. Notice that they are very, very close. Matter of fact, the smaller s goes, the smaller the argument becomes, or s becomes, the closer the sine of s equals s. So for very small s, we actually have that the sine of s is approximate s, but only when s is in radians. For part B, we want to find the exact value of s in the interval 3 pi over 2 to 2 pi if tangent of s is equal to negative root 3 over 3. Now notice that this quadrant is quadrant 4. As a consequence, x is greater than 0 and y is negative. Or x is positive and y is negative. Furthermore, we can write tangent of s in its non-rationalized form, which would be negative 1 divided by the square root of 3. Well, if that's the case, then we would have that this is equal to y over x, and we would have that y over x is equal to negative 1 divided by the square root of 3 in quadrant 4. Okay, well, let's actually look at a point in quadrant 4 which will produce for us this ratio. So let's come to a unit circle. And we can use this one. And if you look at this particular point right here, okay, well, this is 11 pi over 6, and if you notice, we have root 3 over 2 divided by 1/2. And if we actually took the tangent of this, we would get negative 1/2 divided by root 3 over 2, which would reduce to negative 1 over the square root of 3, which is kind of like what we're looking for. So it turns out that this value of x over y being equal to negative 1 over the square root of 3 is equal to this point on the unit circle. And the arc length of this point, or the angle of that point, is 11 pi over 6. So we have that the tangent of 11 pi over 6 will produce for us negative 1 over the square root of 3 or negative root 3 over 3. Therefore, S must be 11 pi over 6. Now we're going to talk about one application of circular functions, and that is linear angle and speed. And we all know what linear speed is. Linear speed is nothing more than the displacement or distance traveled divided by time. Well, in this case, we're restricting the distance to spinning around the unit circle. That's kind of equivalent to the wheel on your bicycle spinning or the wheel in your car spinning. If this point is spinning around the unit circle, then this angle is also spinning around the unit circle. It's also spinning around the unit circle, and it is displacing a certain amount of radians, which we will call theta, as a function of time. And as a consequence, there is an angular speed. And that speed is how much this angle is changing, and we will call that theta divided by time, where once again, theta is in radians. We have a variety of formulas or that we can use to work between angular speed, which once again is always going to be omega, is typically described as omega, and it has per unit time in radians, and linear speed. So here we have our linear speed is equal to our arc length divided by time. Well, we know that our arc length can be written as r times theta if we actually have a circle of radius r, which I didn't specify in this particular case. We're no longer dealing with unit circle. That now has a certain radius. Okay, well, we can actually write this as r times the quantity theta over t. So these are our relationships between linear speed and angular speed. And these are actually just one of the number of dual relationships between what we call linear displacement and angular displacement or rotation. And we can use these for some examples. For example, and here's our first one. Suppose we have a point on a unit circle with radius 15 inches and a ray OP which is rotating with an angular speed of 12 radians per second. So in this particular case, R is 15 inches. And this thing is moving with a speed of pi over 12 radians per second. Okay, so let's go back to the problem. For part A, we want to find the angle generated by P in 10 seconds. Okay, well, we know that omega is equal to theta over t. We know what omega is, we know what t is, but we need to figure out what theta is. So the first thing we can do is solve for theta. And that will give us that theta is equal to omega t. Okay, well, omega is pi over 12. T is 10 seconds. And that will give us 10 pi over 12 radians. We have here a common factor, 10 and 12 have common factors of 2, so this will reduce to 5 pi divided by 6 radians. Okay? Now, for the second part, we want to find the distance that P traveled along in 10 seconds. Now, to solve that, since we are basically on a circle of 15 inches, we can use our definition of the radian, which is that theta is equal to the arc length divided by r, or that r times the radius times the theta is equal to the arc length. We know the radius is 15 inches. We know theta is 5 pi over 6, so we can go ahead and substitute. We will have 15 times 5 pi divided by 6. We can actually simplify this. Notice that 5 and 6 have common factors. That happens to be 3. So this can be written as 5 times 5 pi divided by 6, by 2, not 6, 2, because we're getting rid of that common factor 3. And that will be equal to 25 pi divided by 2 inches. So that's how far that is how far the pulley went. And then the last question is, we'll find the linear speed in radians per second. Okay, well, we know that the angular speed is equal to pi over 12. We also have the formula that the linear speed is equal to the radius times the angular speed. So let's go ahead and substitute. That will give us 15 inches times pi over 12 radians per second. That will give us 15 pi over 12. We have a common factor of 3, and this will reduce to 5 pi over 4. And the units here, once again, will be inches per second. And there you go. And for our last example, we have this thing. We have a belt that runs a pulley, and the radius of the pulley is 5 centimeters, and it's moving and it's spinning at 120 revolutions per minute. And the question here is, the first thing we want to do is we want to find the angular speed of the pulley in radians per second. Okay, so we're looking for W. We're looking for omega. Omega must be in radians per second. Right now we have 120 revolutions. That is 120 revolutions per minute. So we need to go from revolutions per minute to radians per second. So let's do a little unit analysis and do that. So we're going to start off with 120 revolutions per minute. We know that there are 2 pi radians in 1 revolution. 1 revolution, we have basically an angular displacement of 2 pi radians. So in 1 revolution, we have 2 pi radians. All right? And then in 1 minute, we have 60 seconds. Okay, so here the revolutions cancel. So we're looking for the minutes cancel, and all we have left in units is radians per second, which is what we're looking for. Now when we combine all this stuff, we're going to have 120 times 2, which will be 240 pi, including the pi up there. And then the denominator, we have 1 times 60, or just simply 60. And once again, our units will be radians per second. That kind of gives us some confidence that we actually did this correctly. And then when we simplify this, we have 240 divided by 60 is just simply 4. And so our answer is going to be 4 pi radians per second. And then finally, we want to find the linear speed of the belt in centimeters per second. Well, the linear speed is nothing more than the radius of the belt, of the pulley, because the pulley is moving the belt around, times the angular velocity. And that is going to be 5 centimeters times 4 pi radians per second. And that will be equal to 20 centimeters per second. And there we go. That is it. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.